Okay, so this is, I believe, the 7th lecture of problem solving, Math 331. I think my kids have set a record with, 4 straight days of school. Now they have 5 days off because it's winter break, but at least, no longer snow. So we may be seeing the kids on Friday when we will be talking about the Pythagorean theorem, and there is a reason why I want to talk about this. It is related to problem solving. All right, so let's start with the idea of generating functions. How many of you have seen generating functions before? Okay, so no one has seen generating functions before. So one of the difficulties in a class like this is always, what have people seen? You may have seen these a little bit lurking in the background. It's amazing how many problems can be solved with generating functions. So I'm going to first show how generating functions can solve something like the Fibonacci numbers and give us Binet's formula. Now, this is not going to be a real cause for celebration because we can prove Binet's formula directly. We can use the method of divine inspiration. In fact, if we even write down, let's guess the nth Fibonacci number is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. We can check by induction that that works. In general, it's going to be very hard to be that inspired time and time again. Generating functions is a more mechanical way of doing this. Probably the best way to explain this to you is maybe factoring polynomials. What are the roots to this? Yes?
Negative 4. Oh, sorry, 4.
4 and 3, right. You're giving me the factors of x minus 4 and x minus 3 equals 0. Therefore, x equals 4 or 3. What's interesting is I was doing it this way as well. I don't know if you should do it at 4, 3 or 3, 4. But this is the way I was doing it in my mind as well. How are you able to do this so quickly?
Basically a system of equations that we solve.
I mean, I didn't see anybody taking out a piece of paper. You're doing this all in your head.
A nice system.
You're looking for two numbers that add to 7 and multiply to 12. So you're really looking for, x minus a, maybe x minus r1, x minus r2. And so you want r1 plus r2, or negative r1 plus r2 equal negative 7, and you want r1 times r2 to equal 12. And you're solving this in your head. All right, what if I were to tweak it and write it as x squared minus 17x? What would you do now? Now you'd use the quadratic formula. Why didn't you use the quadratic formula initially? It always works. I mean, when I gave you this, no one went to the quadratic formula. Why not? Wow.
In a beautiful way.
It's not fine. If you say it's gross in a beautiful way, then I can accept that. Right. It is not pleasant to use. If you could avoid using the quadratic formula, if you could just look at it and see the answer, you would clearly much rather look at it and see the answer than use the quadratic formula. But if all else fails, it's not horrible to resort to the quadratic formula. And so if I did give you, we'll keep it up for this one. I can write the roots are x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And you get 49 minus 48, which is 1. So you get x equals 7 plus or minus 1, or 2a, a is just 1, over 2. So you get 8 over 2 and 6 over 2, so you get 4 and 3. So again, the quadratic formula will always work. And it's nice to be able to have something like that in reserve. But if you can just look at it and see an easier way of doing it, go with the easier way. I almost view generating functions as a similar method as something like the quadratic formula. It will work, but it will be a little bit more work at times than maybe just the straightforward divine inspiration inspection. If you can just look at something and see the answer, there's no need to go through the whole rigmarole procedure of this. So let's talk about generating functions. So we will do the standard definition of the Fibonacci's. So f0 is 0, f1 is 1, and fn plus 1 is fn plus fn minus 1. So as soon as I give you this, I have completely specified the Fibonacci numbers. There's no mystery left, right? Now, for practical purposes, if I ask you what's the millionth Fibonacci number, this is time consuming. And I think some of the Project Euler problems we've looked at have involved Fibonacci numbers. You can solve these by brute force by enumerating all the Fibonacci numbers and then dealing with whatever you need to deal with, but it's much easier if you can extract a formula. The horrendous thing about this relationship is that we only know the Fibonacci numbers in terms of their immediate predecessors. So if we want to compute one of the Fibonacci numbers, we need to compute everything up to that point. So we would love a closed form expression and be able to just jump to whatever number we want to study. So the idea is to do something called a generating function. So I'm going to find gx to be the sum, n goes from 0 to infinity, of fn x to the n. How many of you have taken differential equations? Okay, I see one person. Okay, so I'll talk to just you. So in differential equations, did you see series expansions? Where you write down a series expansion, the sum of an x to the n, plug it into the differential equation, get relations for the an's, and then hopefully you can recognize the series expansion as a nice function, or failing that, hopefully at least it converges in some region. And that's a great way to solve an equation. We're going to do something like this. Here is our generating function. And the idea is to somehow get global information about the g's, info, and then have that passed to local info on the fn's. Now, at first, this seems a little bit ridiculous. The reason this seems ridiculous is g of x, our global function, is defined in terms of the Fibonacci numbers, which we don't really know. And so how am I going to get information about this object g of x without knowing the Fibonacci numbers? Do we know the Fibonacci numbers? Yeah, so I saw a hand going kind of like this. We kind of do know the Fibonacci numbers. Why? Well, the Fibonacci numbers are completely specified by this. If I wanted to, because I know the Fibonacci numbers start at 0, I could actually start this sum at 1. Not going to really make much of a difference. And so let's explore what's going on. So one of the big things you learn if you take a differential equations class is you learn about shifting index of summations. So if you have differential equations, you might guess the solution is y of x is the sum of an x to the n. You would then get y prime of x is the sum of n x to the n minus 1. And then what's a little bit annoying is you've got things shifted a little bit off. So this would be the same as the sum of n plus 1 an plus 1 x to the n. And now what would be my range for n? Well, let's be careful. If I take n equals 0, I technically have x to the negative 1. I'm a little bit worried about that, but I've got an n over here. I really have a constant term. So over here, I really should be starting the sum at 1. So I can really start the sum here at 0 to infinity. And now notice that this also has the form something times x to the n. And I can group things together. So if I want to solve, y prime of x equals y of x, I would then have, a sum, n goes from 0 to infinity of, n plus 1, an plus 1, x to the n equals a sum, n goes from 0 to infinity of an x to the n. And then the hope is that the only way that this could work is if the coefficients match up. And what kind of relationship we would get? We would get n plus 1, an plus 1 equals an. Right? Anybody have an idea of what function this might be leading us towards? So this is going to essentially imply n plus 1, an plus 1 equals an, or an plus 1 is my nth term divided by n plus 1. If you're not sure, solve this differential equation directly. What function equals its own derivative? E. Well, not e. E to the x, exponentiation. And the series expansion of e to the x is the sum of x to the n over n factorial. Look, that's essentially what we're getting right here. So this is how series expansions work. We put down some guess, we use a relationship, and then we use that to figure out information about the coefficients. Yes?
Can you explain quickly why you chose to set the derivative of y equal to y?
Oh, this is the equation I'm giving you.
Oh,
This was the example. I wanted to choose the simplest example I could think of that would give me an infinite series and would give me a relationship that where we could solve this by divine inspiration. So I want something where I don't need to do the series expansion. I know the answer. But now by looking at this, I can see, oh, yeah. Here's where the 1 over n factorial is coming from. Each term is 1 over n plus 1 the previous. Now, of course, I could take the 0th term not to be 1. I could take the 0th term to be 0, in which case every term is 0, and the function y identically 0 does work. I could take the 0th term to be 5, and then I would get 5 times e to the x. So you have a little bit of freedom in terms of what the solution is. So I encourage you to go through this really rigorously, write down all the details, write down all the steps. But this is a wonderful idea, this idea of guessing a solution and trying to fill out what's going on. Looks like it's drunk over here, so I'm going to try to fix it a little bit as I move. Okay, so now our goal is we have g of x is the sum, n goes from 1 to infinity, of fn x to the n. Now we want to shift things around a little bit. We know the recurrence relation for the Fibonacci's. Now, the first place we can really start using that is at f2, right? So I can write this as g of x is equal to f1x plus the sum, n goes from 2 to infinity, of fn x to the n. So I am going to go through this in excruciating detail. I apologize. I can't even pretend to be excited about doing this. But I just want to really go through how you would do all the series summations and shifts. Well, I want to write fn plus 1 in terms of fn and fn minus 1. There's a lot of different ways of doing this. I can write this as f1x plus, now over here, I can write it as like fn minus 1 plus fn minus 2. That's the same as the recurrence relation. So it'll be a sum, n goes from 2 to infinity, of fn minus 1 xn plus a sum, n goes from 2 to infinity, of fn minus 2 x to the n. Right. I'm just using the recurrence relation for fn. And I just split the sum. Well, if you notice, I would love to have fn minus 1 x to the n minus 1. So I have an extra x that I'll pull out. So this is the same as f1x plus x, the sum n goes from 2 to infinity, of fn minus 1 xn minus 1. And then for this one, I want to pull out 2 x's. I'll have an x squared, the sum n goes from 2 to infinity, of fn minus 2 xn minus 2. And then if you had taken a differential equations course, then you would have remembered that the rest of the game is just changing index of summations. So I now have n minus 1, n minus 1, n runs from 2 to infinity. I want to have everything in terms of x to the n. So if I wanted to write this as a sum of fn x to the n, I still have my x outside. What's the range of n? 1, because when I put in 2, I get 1. So we go from 1 to infinity. Sometimes people like to put in a different variable here. Instead of n, maybe they'll do an m. But at the end of the day, I want to just collect things. I'll leave it like this. So I get f1x plus this. And then this one, it'll be x squared. And what's my index of summation? 0. OK. Hopefully I haven't made a mistake. Now, what does that equal? g of x. So we get g of x, and we know f1 is just 1 equals x plus xg of x. And what's over here? What does this equal? Also g of x plus x squared g of x. This is absolutely amazing. So we get, if I subtract, I get 1 minus x squared g of x equals x. So I get g of x equals x over 1 minus x squared. So it's worth just letting this sink in. This is miraculous. We have an explicit formula for g of x. And now that we have an explicit formula for g of x, we know its series expansion. We should be able to then pull off the fn somehow. Okay? The question is, of course, is this closed form explicit formula useful for g of x? So, how would you try to use this? And I'm not going to go through all the algebra. There's a limit to what I will do to you in public. But we now have g of x is the sum, n goes from 0 to infinity, of fn x to the n, and it's also x over 1 minus x squared. How could we try to get something useful from the right-hand side? What's your first thought? It may not work, but what's your first thought? That should be your second thought. That's the way that works. Partial fractions works. There's something else that this kind of looks like, and it would feel miserably. If you had a 1 on top, 1 over 1 minus x squared, what does that kind of look like? What could we use to understand this? We could use the geometric series. It's a horrible idea, and I know I'm forcing you to say that. The reason this is horrible is that we would have a sum, n goes from 0 to infinity, of x plus x squared to the n. And what's so bad about this is these two terms have different degrees. You could pull out an x, and if you pull out an x, you would have a sum, n goes from 0 to infinity, of x to the n, 1 plus x to the n. And the problem is, if I want to find the coefficient of the x to the fifth term, I'm going to get stuff from a whole slew of things. Right? So when I take n equals 4, it's going to give me terms going from x to the fourth all the way to x to the eighth. So n equals 4 gives x to the 4, x to the 5th, x to the 6th, x to the 7th, and x to the 8th. So this one term is contributing to too many things. So it might be natural to try to do this using the geometric series formula because you've seen that before, but it's not going to work well because these have different degrees. The way to go about it is to factor the denominator. And so, because you've already yelled partial fractions, I will just go straight to the punchline. If you were to ask calc students, of all the techniques of integration, which do you hate the most? The only time partial fractions doesn't come in first place is when people forget that they had done partial fractions. That's how much they just block it out of their mind. But it's a fabulous technique. And what you would do is the x up top doesn't really matter. We have 1 over 1 minus x squared. We write this as 1 over 1 minus ax, 1 minus bx. You can factor the denominator. And then we'll get like alpha over 1 minus ax plus beta over 1 minus bx. And we just have to find what the roots are. If you notice, this is very similar to the characteristic polynomial of the Fibonacci numbers. Instead of having x squared minus x minus 1, we have 1 minus x squared. This is basically telling you it's like the reciprocal roots of the Fibonacci equation. And in fact, you can see that it's reciprocal because instead of having things like x minus r, we have 1 minus ax. So I'm not going to go through the rest of the detail. You find A and B, you then cross multiply, and you'll get alpha plus beta has to equal 1, and alpha times negative B plus beta times negative A has to equal 0. You finish and do the algebra. Do algebra, and you get Fn is 1 over root 5. It's such a beautiful formula, it's worth writing again. 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. And this is Binet's formula. Okay, so this is an absolutely wonderful technique. Not really needed here, because we found a way to get to the solution without going through generating functions. But generating functions can be used for a whole slew of problems. Okay? Any questions on what we've done so far? Yes?
So why did you feel the x, why did you write 1 in the numerator and so just
Over here?
X? Yeah.
Oh, because if I can factor 1 over 1 minus x squared, I can then just multiply through by x.
Okay.
Right?
Yeah.
The x here, it hits both terms.
Yeah. Okay.
So I just pull out the x, and then I have the problem of if I can write the expansion of this, I then multiply both sides.
Sure.
And then the nice thing about partial fractions is the stuff up here is a polynomial of degree 1 lower than what's down here. And so in this case, it's going to be constants because I have 2 roots and they're distinct. I do not want to go back into the general theory of partial fractions. I have had to use this in some of my research papers. It is a wonderful technique for attacking problems. It's worth knowing. And so it's not just sadistic teachers you've had in your past. They may be sadistic, but there's at least a reason for learning something like partial fractions. Okay. Any questions about this? Again, I urge you to go through and do the details of this. Let's do instead of going straight to the Catalan numbers, let's do another example of generating functions. I'll see if I can do this on the spot. But it's related to something we've done earlier in the semester. Anybody remember my favorite combinatorial problem? And if you're going to grad school, it's extremely useful to know this problem. It is the cookie problem, right? How can you divide 10 cookies among 5 people? We will assume the people are distinct and the cookies are not, right? We saw lots of ways to solve this. We saw the one-line combinatorial solution. It's sometimes hard to see that. And so we saw a good way to get to that was to look at simpler cases and start getting intuition and saying, I'm beginning to see a formula. And we did some numerics, we wrote some programs. Right? There's other ways to get there, and one of the ways is generating functions. What we're really doing is we're trying to, so we'll do the cookie problem and cookies. So we want to solve, x1 plus x2 plus xp equals c. Each xi greater than or equal to 0 is an integer. This is the cookie problem. How many ways can we divide C cookies among P people? The people are distinct, the cookies are not, and you can only have an integral number of cookies, and you cannot leave any cookies undivided. Okay? This is called a Diophantine equation. So Diophantine equations are basically equations involving variables that take on just integer values with just nice integer coefficients. If I had rational coefficients, I just cleared denominators. So I can always assume my coefficients are integers. Now, this one, it turns out we could solve this directly combinatorially. There are other ones that we can't solve directly combinatorially. If I were to write this as a sum of squares equals C, we can't solve that combinatorially anymore. The problem becomes much, much harder. Another way of looking at this is which numbers C can be represented as a sum of P non-negative integers. It's not that difficult. Every number C can be represented as a sum. What about sums of squares, sums of cubes? And it's a deep theorem as to how many P do you need to be able to write every number as a sum of squares? How many p do you need to write every number as a sum of cubes? A related problem might be, okay, there could be a couple of numbers that are just problematic because they're small. Maybe I want every number from some point onward to be representable. Is there an answer like that? And so I'll post some stuff about Waring's problem if you're interested. It turns out once once the coefficients of the exponents become more than 1, once they're at least 2, we can't do it elementarily with combinatorics. The best way we have is, in my mind, the most beautiful method in all of mathematics, the circle method. It's a way that makes these problems accessible. And if you are interested, I'm happy to talk to you about the circle method. This is a class in problem solving. How do you attack something like this? How do you attack writing something as a sum of squares? How do you attack something such as showing that there's infinitely many twin primes? And so the circle method, or how do you do something like Goldbach? Every large odd number is the sum of at most 3 primes. We've finally proven that. And anybody know what large means here? Every large odd number is the sum of at most 3 primes. What do you think large is? If you say at most, large is 3. 1 is not a prime. I'm sorry, we can't write 1 as a sum of primes. 3 we can write as a sum of at most 3 primes. 5 we can do, 7 we can do all of them. If you say exactly 3 primes, then it has to be 7. So we can now show every odd number is the sum of 3 primes. We believe every large even number is the sum of 3 primes. Anybody have any thoughts as to what, I'm sorry, is the sum of 2 primes? Anybody have any thoughts as to what large is for even? 4. And so the circle method allows us to attack problems like this. And so if people are interested, let me know. I'm happy to give a lecture or two on how you can actually convert something like this to something where mathematics can help. So let's consider g of x equals 1 over 1 minus x equals 1 plus x squared plus x cubed, etc., etc., etc. Okay? So this is just the geometric series formula. Have we done a proof of that this semester yet? Are we comfortable with the geometric series formula? All right, so we have the geometric series formula. Let's look at g of x squared. This is 1 over 1 minus x squared. And this is the sum of x to the n. N goes from 0 to infinity. And the sum m goes from 0 to infinity of x to the m. So clearly, it's got to be something of the form x to the k. Right? And I'm going to call it a to k. Yeah. Or I could have called it ak of 2. It doesn't matter. The 2 is because we have 2 things. And the k is going to be because it's going to be the kth term. Can somebody tell me what a2k counts?
I think basically the number of combinations of n and m that add up to the.
Yeah, the only way I can get like an x to the 10 is n plus m has to equal 10. So this is the number of pairs nm such that n plus m equals k. That's the cookie problem. If I were to do this cubed, I would have 3 terms. I would have an a3k. Or more generally, if I do this to the pth power, now I want to use better notation. I'll call this n1, x to the n1, n2, x to the n2, dot, 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 sum np goes from 0 to infinity, x to the np. And now, all that changes here is this becomes a p. And now, this is just the number of tuples n1 and p such that n1 plus dot, dot, dot plus np equals k. the coefficient of this is our answer. Sadly, we don't have a formula like this for sum of squares. But this is an analytic approach to the cookie problem. Now, this is useless unless we can figure out a nice way of what is the kth coefficient or the cth coefficient of this. So for extra credit, find the coefficients. So what I've done here is I've hopefully motivated generating functions. This is a way to solve the cookie problem. This is something we've seen before, where we no longer have to be clever in terms of seeing that there's a binomial combination going on. Where do we need to be clever? We have to somehow find the coefficients. So I'll leave that as an exercise to you to try to figure out for extra credit, how do you get the coefficient? Now you have a hint, right? You know what the answer is, right? So knowing what the answer is, that could help you figure out maybe how to do the algebra. Maybe it doesn't. But I'm hoping that this gives you an idea of the power of these generating functions approaches. There's also limitations. We can't use them for everything. Okay, any questions now? What I want to do now is I want to turn to Catalan numbers. This is a far harder occurrence relation than the Fibonacci's. And again, the purpose of this class is to just give you general techniques to attack problems in life in general and mathematics in particular. All right, who knows where I'm from? Boston, right. I hate saying nice things about New York City, but I have to admit there's one part of New York City that is better than Boston. And if you say the wrong thing here, if you say the really wrong thing, you will fail this class. So this is not a good time to talk about the glory years of the Yankees or recent Giants' success in Super Bowls. Anybody know what one thing I must tip my hat to New York, or at least a subset of New York, over Boston?
Pizza?
No, please. Can anybody think of anything nice about part of New York over part of Boston? Anybody drive in Boston? Okay, you want to go for it?
Oh, well, New York City's laid out on a field.
At least part of it, at least Manhattan is a really nice grid. You know, Boston, you know, you'll have, you know, Com Ave, and I think Beacon, you know, crossing and changing which one is on top. It's a nightmare driving in Boston. I will admit Manhattan has a beautiful, nice grid. So there's a lot of problems you can ask about grids. And so the problem we want to deal with is certain types of paths. So let's take 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right. So the goal is I want to start here and I want to end here. And I can only walk right and up. How many paths do I have from here to here?
Some of the choose one of either.
Excellent. And will normally be in the case where where it's n by n. So it'll be n, it'll be 2n, choose n. You know, assuming it's an n by n grid. Okay. So this is a really nice formula because essentially I just look at all the different arrangements of the words, of the letters R, NRs, and NUs. And each different arrangement is a different legal path. The Catalan numbers basically look at the following problem. I want to do the same kind of walk, but I never want to cross the main diagonal. So how many paths are there from here to here that don't cross the main diagonal? So Cn is the number of paths that don't cross main diagonal. So My first question is, can you give me a bound for Cn? Can be a really bad bound.
2n choose 2. Sorry, 2n choose n.
Good. So clearly, it's less than 2n choose n. That's the number of total paths. Anything else? Can you give me a lower bound? Can be a really bad lower bound. Zero is a really bad lower bound, but that's really bad. I just want a really bad. Can you do a little bit better than 0?
2.
Oh, 2. Why 2?
Because there are at least 2 that don't cross.
Oh, you're right. The way I phrase it, so you're right, and stay below. On or below. So sorry. The way I phrased it, you are correct. I should say that I only want to be in the bottom part. You know, there's too many Yankee and Giants fans here. I want to stay away from them. I don't want to rub in our recent victories. So given that you can't be on top now, how do you want to refine your 2? What? So, again, whenever you have a problem, write down some quick bounds. Now, there's an extreme difference between the two of them. 2n choose n, this is the largest binomial coefficient. Right? This is approximately 2 to the 2n over n plus 1, maybe, something like that. Well, I think it's greater than or equal to that. Because the sum of all the binomial coefficients with 2n would be 1 plus 1 to the 2n. It's 2 to the 2n. There's n plus 1 coefficients. This is the largest. So the largest is at least as large as the average. So there is an extreme difference in size, 2 to the 2n versus 1. Which do we think is the truth? What do we think the true order of growth is? Can we get better bounds? So one problem is, can we come up with a recurrence relation for Cn? And so if we can find a recurrence relation, maybe we can solve it. So we'll change this from cookies to Catalan. One of the reasons I really like this problem is that sometimes it's easier to introduce auxiliary quantities. So I think on the homework that I'm assigning for this week, you have to solve, and actually, wait, the one that we even handed in, you had recurrence relations for a's and b's together. And then you used it somehow to get a recurrence relation for just one. And it was a lot easier to introduce this extra recurrence relation to describe certain situations than to just try to directly solve the problem. So here, it's actually going to be easier to introduce a new variable. So when we're looking at the paths, we're looking at all the paths from here to here that are legal, that don't cross this line, that stay in the bottom, or land on it but don't go above. One of the great words to use in mathematics is first. The first return, the first hit. What we can do is we can look at all the paths maybe from here to here, such that the first time we come on the main diagonal is at this point. Because if I look at all the legal paths, can I split the legal paths based on first hit? Can two different paths have the same first hit? Yeah. Can one path have two different first hits? No. I first hit at 5, and I also first hit at 12. A couple of years ago, I was actually born twice, according to one of the federal credit reporting agencies. They hadn't realized they had amalgamated me with someone else. And I had to argue with them. I was not born in 1950 and again in 19... But first is a great way to split things. Does everything have to have some first hit? Why? Because you have to end. So we're going to let Bn be all legal paths with first hit at nn. Okay. Now we can start getting some data. if we do C1, how many paths are there for C1? 1. So C1 equals 1. C2, yeah, we could go like that, or once we go here, we go up there, we have no choice. So C2 is 2. C3, is this small enough that we can do by brute force? Well, let's see. We could go, if we go up 1, if we go right 1 and then up 1, from this point onward, how many paths are there? 2. We can see basically like an induction. So that would be 2 if we go here. All right, so we know we have to start off by going right. So the next possibility is to go here. Then we could either go up 1 or up 2. If we go up 2, how many possibilities are there? Just 1. If we go up 1, then we have to go over right 1, and then there's only one possibility. Or we could have gone over 3, and if we go over 3, the only possibility is up 1. Hello?
Is this intro to numbers?
In a few minutes. You're welcome to come in now. You're welcome to come in now. No, it's no problem. We're just doing the end of Catalan numbers. So we have 2, 3, 4, 5. Okay, so if we really cared, could we find more answers? Could we find C4, C5, C6? Yeah. So what we're doing for those who just came in is we're looking at all the number of paths that start in the bottom right of a grid, end in the bottom left, and in upper right, don't cross the main diagonal, stay on or below the main diagonal. And we're going to find a recurrence relation for this, and we're going to see probably next time how to solve this with generating functions. So we have 1, 2, 5. We could do more and more and more. It starts to get more and more painful. What should we do once we have the sequence? What should we do once we have a sequence of integer values? OEIS, right? The high point of my semester was when the founder of the OEIS called me up and asked for help from me and my students on something from the OEIS. I was thrilled for this opportunity. This is a wonderful resource. I'm not sure if this is a verb. OEIS it. One of my thesis advisors said the Cauchy-Schwarz inequality, Cauchy-Schwarz is a verb. You can Cauchy-Schwarz something. When you have a sequence of integers and you're trying to guess the relationship, feed it into the online encyclopedia of integer sequences. Now what you can begin to see is that the arguments we're doing are suggesting a recurrence relation. You were trying to reduce it to something previous. So let's look at what's going on in the general case. So we start here, we end here, and we have some point k, which is going to be the first hit. What must our first step be? Our first step must be right. What must our last step be? Has to be up. And now, what we have is, if you look at it, we have a smaller triangle down here. This one would have been k things. This would be k minus 1. And we look at all the legal paths here, and they can hit the main diagonal here. Because if they hit the main diagonal, they're still staying below this. How many legal paths are there from here to here? CK minus 1. And that will be all the paths that's first hit is here. And then, how many paths are there from here to here? And Cn minus k legal paths. And so the recurrence relation we should get, and we may have an index slightly off, but it should be something like the sum k goes from probably 1 to n of ck minus 1 cn minus k. Right? I'm not explicitly calling this over here Bn or Bk. There's really no need, because I can see so clearly what its connection is to the C's. There's no real point in confusing things by adding another variable. But if you want, this part over here This is really our BK. It's how many paths you go from here to here where the first hit is here. Well, if the first hit is here, we know we have to start off right. We know we have to go up over here. Whenever you have something like this, you want to check this with a couple of small cases. So fortunately, we've calculated as high as 3. So C3 should be, k goes from 1, so it should be C0, C3 plus C1, C2. Am I doing this right? I'm a little worried about this. Oh, wait, we start off with 1, so this should be C2 over here, right? And the next one should be maybe C1, C1. What should C0 be? How many paths should there be from here to here? So we would get 1 times C2 is 2 plus C1 times C1. So we'd be getting 3.
We'll get C2,
Oh, and then we get that again. Oh, good. We get it again at the end. Thank you. Plus C2, C0. So you get 2 plus 1 plus 2. Whew. OK. How confident are you that this is correct? Somewhat confident. What would make you feel better? Try C4, right? Let's compute C4 by brute force. OK? And so do C4 by brute force. Now, the nice thing is I happen to know what the answer is for C4. So we could actually just check. This would tell us C4 should be C0, C3 plus C1, C2 plus C2, C1 plus C3, C0. Right? And what do we get? So C0, C3 is 5. C1 times C2 is 2. 2 and 5, and we get 12. Right? 14. 14. There you go. OK. And now we're trying to do 4. So I believe Cn is 1 over n plus 1, 2n choose n. So this should be 8 choose 4 divided by 5. All right, 8 choose 4. So 8 times 7 times 6 times 5 over 4 times 3 times 2 times 1, 4 factorial, 4 factorial. Those cancel. 4 times 2 is 8. 6 goes into that twice. So we have, and then we get to divide by 5. The 5s will cancel. We'll get 14. So formula is looking pretty good. OK? And again, I'm giving you the answer right now. Cn is 1 over n plus 1, 2n choose n. The reason is I want you to just jump over here and look at the answer. We know it's at most 2n choose n. We know it's at least 1. It turns out it's extremely close to the 2n choose n. This number is growing exponentially fast. Now, in the limit, 0% of paths work. It's not so unreasonable. It should be pretty likely that at some point we cross over. But a huge number of paths will be valid. So my question to you is, how the hell do you solve this recurrence? So I will restore the recurrence which we just deleted. It was, I think, Cn was the sum, k goes from 1 to n, of ck minus 1, Cn minus k. This recurrence is so much worse than the Fibonacci's. It's not of constant depth. The larger n is, the more terms you have. It's not linear. Sums of solutions are not solutions. There is one way to solve this, and you now know how to solve this. How could you solve this? It's my favorite method of proof. Divine inspiration. I told you the answer, right? Now that you know the answer, it's 1 over n plus 1, 2n choose n. All you have to do is prove that this holds. Maybe you prove it by induction or something, right? So it's a nice exercise. Try to prove with the method of divine inspiration that this is the solution. Now again, it is very difficult to be divinely inspired. Not so hard to pretend to be divinely inspired, when you know the answer and you just hide your work. So we will see next class how to actually prove this using generating functions. And the reason I like this is, looking at this, it does not seem clear at all how to guess that, or how to figure out how you would finish the calculation. Okay, good place to stop.